So what I really want to discuss in this session is two algorithms. One is known as extendable hashing and another algorithm known as linear hashing to address the problem of static hashing. Static hashing means I have some fixed structure, the link of the destination structure where I will be inserting my values is the size is fixed and it needs to be known a priori. Which is very hard to do when we are in the context of database, because the number of records very hard to accurately estimate it. So it's better for us to have some kind of algorithm that will grow and shrink the index structure dynamically. That's before I go into the algorithms that can grow and shrink the index data structure, I first want to show you, like, in a very simple way, what I mean by static hashing. Static hashing, I have here an array of fixed size with 4 elements. It can store 4 elements. And here is the values we want to store. So the idea of hashing, I take the value, apply a hash function to it, and then the hash function, after applying it, the result will give me the destination or the index in this context, the array index where I will store this particular value. So in terms of performance, it's super fast because the complexity is O1, like it is constant. The time it takes to locate a particular value in this structure, or to store, or to basically decide where to store it, is a constant, because all I do, I take the value, apply the hash function, and I close my eyes and go to the index that the hash function tells me to go to. So in this context, what I can do, I can use very simple hash function, which is the size of the array, which is mod 4, because I have 4 elements in this array. And then to store the values, I go to the value and say 5 mod 4 is 1. So I'll go to the index 1 and place 5 there. Now for 4, I do 4 mod 4, which is 0. So where do I place 4? In element 0, in the element with the index 0. So these two are done. 7 is left. Now 7 mod 4 is 3. So I go there and basically find the element, put the element there. And 10 mod 4 is 2, so 10 goes there. So if somebody comes along and say, please give me the record with the value 10, all I need to do, suppose this is just in reality, in the context of database, this will always be a key and value. A key being the value of the key, and key and pointer, and the pointer being some disk block. So if somebody comes along and say, please give me the location of a record with the ID 10, all I do, I take the key, apply the hash. So 10 mod 4, 2, close my eyes and go to element 2, I'll find there the value that I'm looking for. So now if I insert any other record, let's say 20. So 20 mod 4 is 0, yes? 20 mod 4, because 5 times 4, 20, and the remainder 0. So 0, if there is space, I will put 20 in there. If there isn't, let's suppose this element or this element only store one value. In that case, I have to create what is known as an overflow page to store 20. Yeah. So the problem here, this overflow page will defeat the purpose of having a very fast way of locating where my records are. So in this case, if I have an overflow, I have to first look into the primary bucket. If I don't find the value, I have to go to the overflow pages. So ideally, plus if we keep adding more to this table, we will have a lot of overflow pages or overflow buckets, and this will cause degrade the performance. So instead of having this static sized structure, we want some structure that will grow dynamically. And this is where extendable hashing and linear hashing comes in. So let me try to explain this extendable hashing and linear hashing used through an example. And then we go through the generic or the general formulation of the algorithm. So extendable hashing, first of all, it uses what is known as directory. A directory is nothing but an array. And this array, what this array will have, this array has pointers to buckets. So in here, I will explain this shortly. So this algorithm requires us to maintain a directory. A directory is, you can think of it as an array. What we find in this array is basically has elements, and those elements, they're indexed. Let's say in this case 0 and 1. And here, what I have here, I have buckets. Think of buckets as a page on disk, let's say. Page on disk. And a bucket, it can store multiple values, let's say multiple keys. So in this scenario, I am just putting this simple assumption that a bucket on disk can store 2 values maximum. Yeah. So what I have here, this directory, what this directory is really doing is pointing, sorry, B0, B1. This one is pointing to this bucket, and this one is pointing to this bucket. Yeah. So when somebody is looking for some value, I first look up the this directory. We call it directory. Okay. I first look it up, and then after I look it up, it points me to the disk block or the disk page that has my index entry. It will become clearer as we start using it and building it. So this algorithm maintains a directory. There is also another concept called the depth. So here, all of them have local depth. This is called the global depth associated with the directory. And there is something called the local depth, which is associated with the bucket. So I have 2 things. I have a directory that maintains pointers to buckets, and I have buckets where I store the actual index. My actual index will be stored in these buckets. Okay, and this number here 1 is called local depth and global depth. Its role will become clear as we move forward. So for now, just keep it. Let's take it this way. We have a directory pointing to buckets, and we have buckets where we will be storing our values. Okay. Now in here, the size of the directory is 2. You can see here I have two pointers pointing to 2 buckets. So I will be using a hashing function of mod 2. I'll be using a hashing function of mod 2 to try to decide where these values will be stored. So if I take, let's say, the first value, which is 1, so 1 mod 2 is, no, 1 mod 2 is 1, okay? So where is the mod is basically the remainder of the division. So 1 mod 2 is 1. So the value 1 will be stored in B1, in the bucket 1. So 1 is done. We move on and we look at value 16. So 16 mod 2, 0. So 16 will go here. Yes? Okay, 16 is done. 20, apply to it the hash function. 20 mod 2 is 0. Okay, so 20 will go here. 20 is done. 7 mod 2 is 1. So it will be stored here. Okay, now, so basically this, if you look, another way to look at it, you see this, this is called the local depth. this global depth, this is the local depth. Now the local depth is nothing but the binary representation of the hashed key. So what I mean here, if we take 16 and we do mod 2 is what? 0. What is the binary representation in this case? Is 0. Okay, so basically this is the binary representation. This is the rightmost side of the binary representation, because in this case it's the same value. Now same thing for 20 mod 2 is 0, so the binary representation is also 0. While 7 mod 2 is 1, and what is the binary representation of 1? Is 1. So basically this one, all I do, I'll take the way I decide which lucky bucket that will get the actual value. I take the value, hash it using the hash function, in this case mod 2, get the value of that I get after applying the hash function, convert it to binary, and then the first in this scenario, you know, this value here called the global depth, it tells me how many bits should I consider to decide which bucket to store the index in. Because I am the bucket, the depth, the global depth is 1, so basically I am considering only the rightmost digit in the binary representation. Okay, it'll become clearer maybe as we move forward. So now 7 is done. Let's now take a look at 27. 27 mod 2 is 1. Okay, so we will be storing it here, but we put here an assumption that the bucket size is 2. So I can only store 2 values. So when this happens, when I want to store 27, what will happen is I will have an overflow page to store 27. Now, this algorithm, extendable hashing, as soon as there is an overflow, this will cause growing of the index. So the way it grows is we take this directory here, and we basically double it in size. How do we double it in size? We take it as it is, current state. We take the current state of the directory and replicate it. Yeah. So what I mean, let's try to do this. Replicating it means I create exactly the same copy of what is above. So this will be 0 and 1. And this is still pointing to B0, and this one is pointing to B1. Yes? Okay, now to make this uniquely identifiable, this directory entries, to make them uniquely identifiable, all I do, I come here and put zeros in front of these guys and ones in front of this. Yeah. Now, what will happen to this global depth is basically 2. 2 means I am considering from now on, because my directory has grown, from now on I'll be considering 2 binary digits to decide which bucket I will be placing the index into. Okay. Now what's happening here? This bucket, basically now what we have now, we have pointer 0, pointer 1, pointer 2, and pointer 2 and pointer 3. Sorry, pointer 3. Okay, so pointer 0 is pointing to bucket 0, pointer 1 is pointing to bucket 1, pointer 2 is pointing still to bucket 0 because we copied it, remember? And bucket 3, pointer 3 is pointing to bucket 1. Yeah? Okay, so this is the first step. The first step, we take our directory, we double it in size. How do we double it in size? We literally copy it over as it is, copy, increment, of course, like in here, make it uniquely identifiable by adding zeros to the previously existing directory entries, and 1 to the ID of new buckets. And then we increase the global depth by 1. So it was 1, the global depth was 1, now the global depth is 2. Then we come to this troublemaking bucket, which is B1, and we split it. What I mean splitting it, we create another copy. We basically create another bucket. We create another bucket, and then we redistribute the values of this bucket that was split. So this one is bucket one, sorry. When we split it, it basically becomes bucket 3, okay? And these, because we split this one, these become basically, these are, the global depth will increase as soon as we split the bucket. Sorry, this is called the local depth. The local depth is also increased. And in here, this is B3. So P3 is no longer pointing to no longer pointing to B1. It will be pointing to B3. Yeah. And this, because we haven't split B0 yet, so pointer 2 is still pointing to B1. So B0. So B0 has 2 pointers. One from the old entries of the bucket of the directory, and there is a new entry also still pointing to B0 because B0 is not split yet. Okay. So what we do to summarize, after the doubling the directory, we go to our buckets that caused the overflow and we redistribute the values. But now, because now we have 4 entries in the directory, our hash function becomes mode 4. Okay, so let's redistribute these values using the new hash function. So one mode 4 is 1. Yes, so it will remain there. Okay, so it will remain there. No problem. 7 mode 4, 3. So 7 mode 4 is 3, so we remove it from here and we move 7 here. Yeah. Now 27 mode 4. 3. Yes, 24 and 3. So this will be removed from here and placed here. And we get rid of, there is no overflow. Is clear so far? So to summarize, I started with 2 buckets, which means 2 disk blocks to store my index entries. And then because I have only 2 buckets, the hashing function will be mode 2. I keep filling these buckets. When they are full, and one of them need to be overflown, will cause an overflow, then it's time. This will trigger doubling the size of the directory. So I started with 2 buckets with a directory with 2 entries pointing to 2 buckets. I go to my directory and double it in size. How do I double it in size? I take it as it is, copy it over, and then basically the IDs of the directory, the IDs of the entries, the initial ID, the existing buckets before doubling will maintain their IDs by adding 0 in front of them, and the new directory, the new entries that were created through copying, I put this digit 1 in front of them. So now every index in this directory is uniquely identified. Okay, then I'll go to and increase the depth. I started with the global depth of 1. After doubling, I increased it to 2. And this global depth, the meaning of this global depth is basically this is the digits, the number of digits I consider to decide which bucket I'll store the index into. So what I mean here, for example, let's take 27. So 27 mode 4 is what? Is 3. What is the binary representation of 3? 1, 1. So that's why I need to use 2 binary digits for me to decide which bucket I will store this key of value 27. So that's why I increased this. Now, when do we increase the global depth indicator or the global depth value? We increase the global depth value whenever we double the size of the directory. And when do we increase the local depth? Whenever we split the bucket. Okay, so this bucket caused an overflow. That overflow triggered doubling the size of the directory, and of course it triggered splitting the bucket. Now when I split it, I increased the local depth to 2 because this bucket now is identifiable as 0, 1, and this one is identifiable as 1, 1. Okay, and then I'll go ahead and the values I had here, I basically hash them with the new hash function, which is mod 4. So you remember, every time I double the directory, the hashing function will change. It starts with mod 2, then mod 4, mod 8, mod 16, mod 32, and so on. Okay. Now, in here, there is no need to do any redistribution because there is no overflow. And even if we do mod 4, let's say somebody is looking for the value 20, for example, we do 20 mod 4 is 0. Yeah, so we find it there. And 16 mod 4, 0 is still in the same bucket. So although we move to a new bucket, there's no problem. Yeah, even if we happen to land here into P1, the P1 is still pointing to B0. So we will always find the values even if we use the new hashing function. Okay, so let's move on. So far, what did we store? So far, 27 is done. Let's do now 29. 29 mod 4, 1. Yeah, so here is bucket 1. I put there 29. 18 mod 4, 2. Yeah, 2. So basically 2, here is pointer 2, is still pointing to bucket 0. So I'll come here and say there is no space. I want to store 18, so this will cause an overflow. And what the overflow will trigger? Are we going to double the directory? Before we double the directory, what we do is we go to this local depth, compare it with the global depth. If the local depth is less than the global depth, we don't double the size of the directory. All we need to do is split that bucket. So here is B0, the corresponding kind of split version of it. The corresponding split bucket will be, B2. Okay, so this is B2, and so I split this one, so the local depth will be 2 here. And now, because after splitting, this pointer here no longer will be pointing to B1, it will be pointing to, basically it will be pointing to B2. Yeah, okay. Now what we do is we redistribute these values using mod 4. So 16 mod 4, 0, it will remain there. 20 mod 4, 0, it will remain there. And 18 mod 4, 2, so this overflow will disappear, and 18 will come here. It's clear so far? So when there is an overflow, when an overflow occurs, so what we do, we look at the local depth associated with the bucket, compare it with the global depth associated with the directory. If the local depth is less than the global depth, we don't need to double the directory. All we do is split the bucket, we adjust the pointers, and also we increase the local depth by 1. So local depth is now 2 in both. Okay, moving on. So 18 is done. Now 11 mod 4, 3. Okay, so bucket 3 is full, so this 11 will cause an overflow. Yeah, and because this is an overflow, what will happen? What this will trigger, this overflow? So what we do, we go and check the local depth, compare it with the global depth. Is the local depth less than the global depth? No, so they are equal. So what this will cause? This will cause doubling the size of the directory. So how do we double the size of the directory? So literally, we go ahead and copy it over. So this directory has 4 entries, so new 4 entries will be added. Okay, so we copy it first as it is. So 0, 0, 0, 1, 1, 0, 1, 1. Yeah, and this one was B0, B1, B2, and B3. Yeah, and this one is P4, P5, P6, and P7. And to make everything unique, I'll have to put here 0, 0, 0, 0, and here 1, 1, 1, 1. And what happened to this global depth? This global depth will become 3. So whenever I double the size of the directory, the global depth is incremented. Yeah. Okay, and what is my new hash function? Mod 8. Okay. Now, which bucket has caused the overflow? B3. So the corresponding bucket is always plus 4 because the size of the initial directory is 4. So the corresponding bucket will be B7. So I'll create here. Let me just go ahead and create here B7, and because we are splitting this, we increment the local depth to 3, and the local depth is 3. So P7 is pointing to B7. The rest are still pointing to the old buckets, okay? And now what we do is we redistribute these values. We only redistribute the values of the bucket that was overflow, not the other ones. The other ones, we don't touch them, okay? So we'll ask ourselves, 7 mod 8 is 7. So this will be removed from here and placed here. Yeah, 27 mod 8. So it's 3. So 27 will remain there. And then 11 mod 8, 3. 11 will remain there. Okay, and then we don't have an overflow. Yeah. So to summarize the algorithm, so we start with the directory pointing to buckets. We start whenever we start with the hash function mod 2, and then we keep filling our buckets. Once they are full, we go to the bucket that caused the overflow. We check the local depth of the bucket. We compare it with the global depth. If the local depth is less than the global depth, all we need to do is split the bucket that caused the overflow. That's all we need to do. If the local depth is equal to the global depth, what we need to do? Double the directory by copying it over. Okay? Double the directory, increment the global depth, go to the bucket that caused the overflow, and split it. When we split it, we also, of course, increment the local counter and apply a new mod function. Whenever we double the size of the directory, we apply the new mod function. New hash function. The hash function is always mod the size of the directory. So you see here the size of this directory has 8 entries, so the hash function is mod 8. Yeah. So let's see more examples. So hopefully it will become clearer. So did we how we go in with 11? 11 is done, yes. 22. 22 mod 8. 22 mod 8. Yes. 22. Yes. So 16. 6. Okay. 6. So it says here P6 is still pointing to bucket 2. Bucket 2 here. No problem. It has enough space, yes? So we just go ahead and put 22. 22 is done. 28 mod 8 is 4, yes? Okay. 4. So we go here, B4. P4 is still pointing to B0. Can you see it here? P4 is still pointing, because we went and said 28 mod 4 is 24 mod 8. Yes, sorry. Yes, it is 0. So 24 mod 8. Yes, it's 0, sorry. I keep confusing. So 0, so we need to put it in here, yes? We want to put it in here, but unfortunately this bucket is full. So what this will cause an overflow. Sorry, 28. 28. When we want to put 28, this will cause an overflow. Then when this overflow happens, what should we do?
28 or 24? You say 24.
No, sorry, I meant 28.
But 28 is not 0. 28 mod 8
Is 4. Yes. Yes, yes, you're right. Is 4, so this P4, because it hasn't been split, P4 is still pointing to B0, yes? So although it's 28 mod 4, yes, you're right. 28 mod 4 is 4. We go to pointer 4. Pointer 4 is still pointing to B0. We go to B0. The B0 is full. This will cause an overflow. So what we do here, what this will trigger, before we decide whether to double the size of the directory or not double it, we look at the local depth, compare it to the global depth. If the local depth is less than the global depth, what should we do? No, just split the directory, split the bucket. When do we double this? When do we double the directory? When the local depth is equal to the global depth. In this scenario, what is the local depth of bucket 0, B0? 2. And what is the global depth? 3. Yeah. So we just need to split this one. So when we split this one, what we will do, we will create a B4, bucket 4, and the depth of this one will be 3. And the depth of this one will be 3. After splitting, the local depth gets incremented. Okay, and then what we do here, this one no longer pointing to B0, it will be pointing to B4. All right, now here is B4, and our hash function now, our hash function is mod 8, so we redistribute these values. So 16 mod 8, 0, so 16 will remain there. 20 mod 8, 4. Okay, so 20 will be removed from bucket 0 and moved to bucket 4. Yep. Now 28 mod 4, 4. So it will be removed. This overflow will be removed, and basically 28 will be placed here. Yes. And by the way, this global depth, it means how many bits we use to decide which bucket we will be using. So in the case, for example, of 28 mod 4 is 4. What is the binary representation of 4? 100. Okay, that's why. So this 3 always represents the binary representation of the hashed value. The binary representation of the hashed value. Okay, so 28 is done. 9 mod 4 is 1. So here B1. So do we have space? No. So this is by the way 1, and this is 29. Well, so this will cause an overflow. 9 will go here. This will cause an overflow. Once an overflow happens, what we ask ourselves? Compare the local depth with the global depth. What is the local depth of B1? 2. What is the global depth? 3. 2, the local depth less than the global depth. Do we need to double the directory? No, we just need to split this bucket. So this will create B5. This will create B5. Here it is. This is bucket 5. The local depth is 3. We increment this one. The local depth is 3. Okay. And then basically this bucket here, yeah, this bucket,
So here is 9 mod, you said 9 modulus.
sorry,
The number we're doing now is 9.
yes, modulus 8 is 1. Yeah. Okay, so what we do here now, so sorry, this one is now pointing to B5. Yep. Okay, now what we do here, we redistribute the values using mod 8. So 1 mod 8 is 1, so it will remain there. 29 mod 8, 29 mod 8 is 28, 1, yes? Because 4 times 8, no, 32. So 24, yes, it's 4. It's 5, sorry. No? 20, yes, it's 5, yes? It is 5. So it will be removed from there and placed here. And 9 mod 8, 1. So 9 will remain there. Yes? So what I mean here, all we need to do, whenever we have a new value, we apply the hash function. If we land in a bucket, if there is a space, we place the value there. No space, this will cause an overflow. To avoid the overflow, we basically need to grow our index structure. How do we grow our index structure? Either it is through only splitting the bucket or through doubling the size of the directory and splitting the bucket. When do we double the size of the directory? If the local depth is equal to the global depth, we have to double the size of the directory. If the local depth is less than the global depth, all we need to do, split the bucket. That causes the overflow. Of course, when we split the bucket, we increment the local depth, and we redistribute the values of that bucket that's overflown. We redistribute its values using the new hash function. And some values will remain in the original bucket, and some values will be moved to the new bucket that was created. So this way we are growing. You can see here, our hashing is not static. Our hashing is dynamic. Our hashing function changes, and the size of our data structure also change. That's what it means by extendable hashing. So it's not static. It's not like the original case. In here, it's always mod 4, and causing more and more overflow pages. In here, as we enter more values into our index dynamically grows. Hash function dynamically grows. That's what extendable hashing is. I think the last value, 9 is done, yes? Last value is 14. 14 mod 8. 14 mod 8, 6, okay? 6. So here, pointer P6. P6 is pointing to B2. B2, yes, B2 here. So it's still pointing to B2. B2 was not split yet, okay? So what I have here, so I'll try to put, which value are we trying to put? 14, yes, 14. So 14 is still, you see here, it resolved to P6, and P6 says, oh, I am still pointing to B2 because B2 has not split yet. So this will cause an overflow if I try to put here 14. Okay, so now, because I don't tolerate with this extendable hash, and I don't tolerate overflow. So what this overflow will cause? Either definitely it will cause splitting of the bucket that's overflown, but it might also cause doubling the size of the directory. How do we decide whether we doubling the size of directory or no? Based on this metadata that we capture in the index, local depth versus the global depth. What is the local depth of B2? 2. What is the global depth? 3. We are lucky now. The local depth less than the global depth. We don't need to double the size of the directory. All we need to do, split the bucket. And the corresponding bucket will be B6. Sorry, it's supposed to be here. So this is my B6 here. And its local depth is 3. I also increment this local depth to 3. This pointer now is no longer pointing to B2. It will be pointing to B6 because we have splitted B2. Okay? So this will be pointing to B6. And now what is left is to redistribute the values of B2 using mode 8. 18 mode 8, 2. 18 will remain there. 22 mode 8, 6. So yes. So 16 plus 6, 28. So 22 will be removed from B2 and moved to B6. And 14 mod 8 is 6. So it will be, the overflow will not be caused, and 14 will come here. That's basically what extendable hashing is. So the algorithm maintains the directory. Directory is nothing but pointers to the index buckets. When I say index buckets, those are index pages. Those are pages in disk. When I want to add an entry, to the index, I apply the hash function and look up the directory. The directory will tell me which lucky bucket where I should place my index entry. I go to that index entry and say, do you have some space? If there is space, I just place my index entry there and that's it, finish. If there is no space, this may cause overflow. And extendable hashing does not allow overflow. So this will trigger two things. Either we just split that bucket that caused the overflow. When do we just split without doubling the size of the directory? When the local depth is less than the global depth. Now, if the local depth is equal to the global depth, before we split, we need to double the size of the directory, increment the global depth. When we increment the global depth, we change the hash function. If it was, let's say, mode 2 becomes mode 4. If it was mode 4, it's doubled. The directory is doubled, and our denominator of the mode function is also doubled. Okay? And then we also go to the bucket that caused the overflow. We split it. We increment its local count, its local depth, and we redistribute the values using the new hash function. Yeah? The other buckets, we leave them alone because no problem. Although the directory was doubled, the new entries in the directory still pointing to all the buckets. Yeah? And we keep adding values to the index. If we land in a bucket that, if we try to insert into a bucket and this insert causes an overflow, we always check the local depth. If it's less than the global depth, we just split that particular bucket. If the local depth equals the global depth, we double the size of the directory, then split the bucket. I hope it's clear. So you need to practice it by hand and really think about it for you to grasp it 100%. Okay, so now let me just quickly introduce the other one, which is the linear hashing. So there is extendable hashing, and there is something called linear hashing. Now, linear hashing, first of all, it does not have a directory. So extendable hashing has a directory. It's an algorithm somebody came up with, and linear hashing is something much better than extendable hashing. First of all, we don't need to maintain a directory, and when we grow, we don't grow exponentially by doubling the directory. We just grow by adding one bucket at a time, as we will see shortly. So in this algorithm, all what we have, okay. So in this algorithm, okay, what we have is basically buckets. Let's say B0 and B1. Yeah. Okay. We have a hash function. We start with the initial hash function, which is H1. In this case, because we have two buckets, we have the hash function will be the key mode 2. This is our first hash function. What we have, we also maintain, this algorithm maintains a pointer called next. Next is pointing to the bucket that will be split if there is any overflow. If there is any overflow, we will go to the bucket that has the pointer pointing to it, the next pointer pointing to it, and we split that bucket that has the pointer, and we move the pointer down, as we will see shortly. Okay, and here we started with how many buckets? We started with n0 equal to 2. So these are the entries, and we also have the bucket size. The bucket size is 2. We can only store 2 values in this bucket. So let me summarize. I started with 2 buckets, bucket B0 and B1. A hash function 0, which is mod 2 because I only have 2 buckets. And n0, which is 2, I started with 2 buckets, and that is a constant thing. That's the size, that's how many entries I can fit in one particular bucket. Okay? So now let's start looking at inserting these values into the index. Okay? So we'll take 1. 1 mod 2 is 1. 1 is done. 16 mod 2, 0, so 16 will go there. And then 20 mod 2, 20 will go there. 7 mod 2, 1, and the value will be here. Okay, so any new entry will cause an overflow. Okay, 27 mod 2, 1. So this will cause an overflow, and basically 27 will be placed there. Okay. Okay, now what the overflow says, so what the overflow will trigger splitting a bucket. But which bucket will be split? The one having the next pointer, not necessarily the one having the overflow. So the linear hashing tolerates temporary or transient overflow. This overflow at a certain stage will be split and we will get rid of it. But when there is an overflow, we don't go and split the bucket that caused the overflow. With which bucket do we split? The one having the next pointer. So initially, which buckets are we going to split? B0, okay? B0. Now, so basically the splitting goes into a rounds, several rounds, okay? Now we started here, we started with round 0. And by the way, these are the values we are using for round 0. For round 0, we started with the number of buckets, two buckets. We started with the hash function h0, which is mod 2. Now, what the splitting will be done, the way we do splitting, is we will first introduce a new hash function, which is basically key mod 4. So basically, we will be using 2 hash functions at the same time. 2 hash functions at the same time. Initially, all of these buckets are using the same hash function. Initially, all of them are using h0, which is mod 2, mod 2. Yeah. Now, because of this overflow, we have to split this bucket. So the way we split it, we create another bucket here, and this will be B2. Okay, this is B2. And basically what we do, this bucket that is split will be using a new hash function. Sorry, not that one. That one is still using, this one we don't, oh no, yes, this is the one, sorry. It is the one, so will be using H1. So this algorithm will be using 2 hash functions at the same time. The bucket that split will use the new hash function. The buckets that did not split will keep using the old hash function. It's a multi-hash function we are using. Okay? Now, what happened is I have a new hash function for bucket 0 and bucket 2 because those are split. And bucket 1, because they did not split, it's still using H0. Yeah? And now, because I'm splitting B0, what I will do with it, I will rehash it using the new hash function. What is the new hash function? The key mod 4. So 16 mod 4, 0, it will remain there. 20 mod 4, 0, 20 will remain there. Okay, no problem. But what will happen to this next? It will move down. Next time we need to split, this is the lucky bucket that will get split. Yeah? And this overflow, fine, no problem. We can live with overflow in linear hashing. We tolerate overflow because we are sure, because we are doing this splitting in a round robin fashion, one at a time. We will get to the overflown bucket at certain stage. So it's fine for short period of time. We can live with it. Okay, so 727 is done, and it caused split of B0, and it caused the introduction of H1. So B0 and B2 are using H1 hashing function, and B1 is still using H0 hashing function. Yes? Okay, so 29. 29 mod 2 is 1. Okay, good. 29 mod 2 is 1, so we place 29 here. So this is definitely making the overflow even worse. So what we need to do? Split the bucket. Which bucket will be splitting? The one that has the next pointer. Not the one necessarily cause the overflow. The one that has the next pointer. So what we will do here, we create another bucket, B3, and guess what? This bucket, which hash function it will be using? H1, and this one, which hash function? H1. And then what we do? We redistribute the values using the new hash function. So 1 mod 4, 1. It will stay there. 7 mod 4, 3. 3 will move, will be removed from there and moved here. Yes? Okay. 27 mod 4. 3. Okay, 27 will be removed from there and placed here. And 29 mod 4, 1. And 29 here. And we now, luckily, we got rid of the overflow. And we split it next. We split it B1. What we do with the next pointer? Because we went through all the rounds. So round 0, did we finish round 0? Round 0 is finished because all the buckets we started with, which is 2 buckets, are split. So now bucket round 0 is done. We move into round 1. We're starting with an N1. How many buckets we have now? 4. Yes? Which hash function we are using in round 1, starting with, in round 1? H1, which is mod 4. Yeah? And what we do with the next? We reset it to 0. Next is now here. Yeah? We start in a new round. So any splits will cause creating another hash function. We'll have H2, and H2 will be mod 8. So we always have 2 hash functions. Now when we finish the round, all of them are using H1. Any splitting will move to H2. And some buckets will remain with H1, and the splitted buckets will be with H2. Is clear? Okay, so let's move on. So 18, remember now that our hash function now is mod 4 for all of them. So 18 mod 4 is 2, yes? 18 mod 4 is 2. We have space, we just put 18 there. 11 mod 4, 3. 3, here is 3. 3 is full because the capacity is 2. This will cause an overflow. No problem, we put the overflow here. This is 11, yes? And the overflow, what the overflow will cause? Once we get an overflow, what this will trigger? Splitting. Splitting what? Splitting the buckets having the next pointer. So what I will do, let me now change the color to this one. Okay. So I'll be creating another bucket here, B4. Yep. So this bucket will be using H2, and this bucket will be using H2 because I split it. Once I split, I move to the next hash function. Yeah, and then I'll be redistributing these values using the new hash function, which is mod 8. So 16 mod 8, 0. 16 will remain there. 20 mod 8, 4. 20 will be moved here. And what happened to the next pointer? We'll be moving down. So next time, if we need to split, which bucket we will split? B1. Okay? Are we done with the 11? With 22, sorry. No, 11. 11 is the one that we did. Now 22. 22 mod 4. Remember, our hash function is still 4. The official one. The original hash function we started with in the round. So 22 mod 4. 22 mod 4 is 2. Yes? Is 2. 28 mod 4 is 22 mod 4 is 2. So we have space here. We place 22 there. No problem. Yeah. 28. 28 mod 4. 6. We forgot our math table. So 0, 7, yes. 7 times 4, 28, 0, yes. Okay, 28 will be here. Oh, yeah. Look at this. 28 will be here. If 28 mod 4 is what? 0. If we land in here, if we land in a bucket that is before the next pointer, we have to apply the second hash function. Remember that B0 is now using hash 2. So we don't just, if we hash a particular value, and that hashing takes us to a bucket that is placed before the next pointer, we have to rehash that value using the new hash function, which means 28 mod 8, 4. Yes, 28 mod 8 is 4, so 28 will be here. So be very careful with this one. So you first apply the first hash function, which is h1. 28 mod 4 is 0. 28 mod 4 is 0 because 4 times 7 is 28, and the modular, the remainder is 0. Now we will land here, which is before the next pointer. If we land here before the next pointer, we must apply the second hash function to really decide the lucky bucket that will receive this value 28. So we cannot just place 28 here immediately. No. We first reapply the new hash function, which is h2, because bucket 0 says I'm using h2. I'm not using h1. So please go ahead and apply h2. So if we say 28 mod 8, 4, and then 28 will land there. Is clear? So 9 mod 4 is 1. No problem. Here is 1. I go ahead and this will cause an overflow. This is 9, yes? This overflow, what will this overflow cause? It will trigger splitting. Splitting what? The bucket that has the next pointer, not necessarily the bucket that caused the overflow. But in here it happens to be both the same thing. Okay, so what does splitting mean? I create a new bucket. Here it is, B5. Yeah, and the hash function for this new bucket is h2, and the hash function of the bucket split is h2, and then I redistribute these values using h2, which is mod 8. So 1 mod 8, 1 will remain there. 29 mod 8 is 29 mod 8, 5? Yes, 29 mod 8 is 5. So this will be removed from there and placed here. Yep. And then 9 mod 8, 1. So it will remain there. And we get rid of this overflow. what will happen to this next pointer? Will move down. Will move down to this. Any overflow now, anything that causes an overflow, what will happen? We split B2. Okay, now let's move on to 14. 14 mod 4. 2, okay? 2. So 2 is full, so I'll put an overflow here, 14. And this will cause a split. It causes a split of which bucket? B2. Not because it's overflown, because it has the next point. Okay, which means I create another bucket here, B6. And this bucket, the hash associated hash function is 2. And the associated hash function here is H2. Yes? And then basically I redistribute these values using the new hash function. So 18 mod 8 is 2. 18 will remain there. 22 mod 8, 6. 6. So 22 will be moved out to here. And 14 mod 8, 8, 6 also. So this will be removed and placed here. And what happened to the next will be moved here. You get the idea? So this is what linear hashing is. There is no directory. There is no doubling of directory. We split linearly. We keep splitting in a round-robin fashion. Whenever we split, we are doing it in a rounds. Around 0, we started with 2 buckets. When we split these 2 buckets we started with, we move to round 1. Round 1 we will have 4 buckets because each bucket in the round 0 will split. We will end up with 4 buckets at the end of round 0. When we enter round 0, when we enter round 1, how many buckets we have? 4. And all of them using H1, hash function 1, which is mod 4. And what we do when we end the bucket, when we end the round, we take the next pointer and put it, initialize it back to 0. Yeah, and then we keep, whenever there is an overflow, we split the bucket that has the next pointer. When we split the bucket, that bucket that splits starts using the new hash function. So at any particular time, we might be using 2 hash function in our algorithm. And the idea here, let me just summarize it through the slides. You can if you want, but okay. All right, just 5 minutes. I will just show you one small little thing. Okay. Just want to visualize this in your mind when we look at the linear hashing. In linear hashing, this is in a particular round, we start with some number of buckets. Sorry, not there. This is the buckets we started. Sorry, this is the buckets we started with at the start of the round. Yeah? Okay, and we have our next pointer. Whenever we have an overflow, we keep moving the pointer down. Yeah. Now, this part here that is already split, it's already using the next hash function. So for example, if we are using H0, this bucket splits already using the new hash function, H1 for example. And these buckets that new ones, of course, are using the new hash function. And what is in between is still using the old hash function. Anything not split is still using the old hash function. Anything split is using the new function. Yes? Anything not split is still using the old hash function. Anything split is using the next or the new hash function. So we have 2 hash functions. Okay, now if we hash a value, particular value, either we are looking up value or we want to insert new value, and the hashing we landed in here. We landed in an area before the next. If we land in an area before the next, we cannot just go ahead and say, let me place let me place the value in the buckets that the hash function told me. No, you have to really not be content with applying the first hash function. You must apply the second hash function. Whenever whenever the initial hash function or the first hash function lands you in an area before the next, you must apply the new hash function, because before the buckets before next, what happened to them? Already split, which means they already moved on to the new hash function. So if your first hash function lands you before the next, don't be deceived. You need to really apply the second hash function to be sure that the second hash function, it can still land you at the same place, or it can land you at some other place, like the new. It can land you either two ways. It can either land you here or here. But if the first hash function, if it lands you here, you must apply the second hash function. Yes? Okay. So when do we move the next pointer? We keep moving the next pointer down, down, down until all the buckets we started with when we started the round are split. When all of them are split, we move to a new round, which means we take the next and reinitialize it to 0. And all of them will be using, when we start a round, all of them will be using the same hash function. As we start splitting, we create a new hash function. And usually the hash function will be doubled. So we start with mode 2, mode 4, mode 8, mode 16. So we have the hash function is doubling, but the buckets, we don't have directory that is doubling. We are linearly increasing our data structure. We are not doing it like in a non-efficient way as we did in the extendable hashing. So linear hashing is much more efficient because it splits. It doesn't. First of all, it doesn't maintain any directory, which is an extra headache, an extra data structure we need to take care of. We have local depth, global depth, a lot of things we need to take care of. In here, we only maintain basically the next pointer. We need to maintain which bucket will be split in next, and we need to maintain which hash function is used by which bucket.